All right, guys. So the thing from the video, the reason why I wanted you to watch that clip was the part with the bookcase. Okay. What's their plan for getting the bookcase upstairs?
I think we should work on that sooner.
They're sliding the bookcase up the stairs, right? So instead of lifting it and carrying it, they're sliding. They say it reduces the force required to lift by half, 50%. So it takes half the thing. Now the other assumption they made was the angle of the stairs. Remember what that angle was? 30 degrees. Okay, so here's the bookcase.
How do they know that just by looking? Are they just made it up? They're very small.
Well, you get used to seeing what 30 degrees looks like.
Oh.
So, and they
Do
probably
you know what 30 degrees looks like for you?
close. And it's a good assumption to
It's
make.
kind of a sharp angle.
All right. So
45.
here's the stairs.
90.
Draw the stairs is just an inclined plane with a 30-degree angle. Okay. Here's the bookcase on this side. Now I know this is not what they're going to do, but if you were to lift the bookcase and just carry it up the stairs, it's a lot like lifting it and just going up the whole distance at the same time. Okay. So let's assume the bookcase is 500 newtons. Let's assume that's the weight. Okay. So what's the force they would need to lift it? 500 newtons, right? Now, this whole problem is predicated on work. Okay? Work is the product of force and displacement. This whole problem is predicated on that. Right? So let's say that these stairs, the landing is 6 meters tall. Okay? So let's say it went to 6 meters. Right? Can you figure out the work needed to lift the bookcase up to that 6 meter height?
How'd they get it up the first flight of stairs?
That was the first flight of stairs that they're showing.
But they weren't in the lobby.
Yeah, they were.
Yes, we can.
So can we figure out the work done?
Yes.
Okay, what do you do, Rex?
But, theoretically.
Okay. So that force is up, right? The displacement's up. They're in the same direction, aren't they? Right, Amani? So how do I find the work?
You do force times displacement.
Okay, so 500 times 6. Right? Does that make sense?
Yeah.
500 times 6, what does that equal?
3,000
3,000. Now, when they slide the bookcase up here, do they do more work or less work? More, less,
Equal.
the same. Okay, so there's 3 options. More or less, the same. Okay? Now, there are a couple forces we need to think about here. Okay? One force we need to think about is a 500 Newton upward force. Now you're probably saying, why do they need that? They're not going straight up like they are on the left side. They're going up the incline. Well, in this situation, 500 newtons is still being applied to the bookcase. Except it's not being applied just by Leonard and Sheldon. Okay, those are the 2 scientists, the skinny guy and the guy with glasses. All right? It's not just being applied by those 2. Okay? There's another thing applying this force. Okay? Which way do Leonard and Sheldon push? Diagonalish, right? Leonard and Sheldon apply a force this way.
But they shouldn't.
Right? So what supplies the rest of that 500 Newton force? The stairs. The stairs have a normal force that's actually perpendicular to the surface, and it's parallel to what's needed right there. So now the combination of Leonard and Sheldon's force and the normal force from the stairs will add to that 500 newtons. You guys see that?
Yep.
You guys see how it's all kind of drawn together right there? Kind of cool, huh? Okay. And that's why inclined planes are helpful for moving heavy objects to new heights. Okay. So it requires a smaller force up the plane combined with the normal force from the plane to equal out that force needed to lift it. Okay, does that make sense? Okay, so either way, 500 newtons is being applied to the bookcase. Okay? Now, they're still going up 6 meters, aren't they?
Yeah.
Okay. But they're not going 6 meters. They're going up the hypotenuse, aren't they?
Yeah.
Okay. So, this is 30. This is 6. It is what to the 30? Opposite, and I hope this makes a right angle. Otherwise, they're in more trouble with their stairs not being or making a right angle. So 30 and 6, right? This is opposite. This is the hypotenuse. So what trig identity can we use? So right. So sine of 30 equals opposites over hypotenuse. Let's call it x. Okay. Can we solve for x?
Yeah, we gotta switch some stuff around.
Switch some stuff around. Do some algebra.
Yeah.
Okay.
So wait up, Locke.
So x sine 30 equals 6, right?
Yep, and then divide by sine 30. And then you get x equal.
6 divided by sine 30, right?
12.
The other hint, Imani, to how they know it's a 30-degree angle is if the height is half of the distance they walk, then it's 30. That's the relation for every 30, 60, 90 triangle. The side opposite the 30 is always half the hypotenuse. So that's another reason why they might know. Okay? That's kind of the hint for measuring seeing a 30-degree angle. If this looks like it's half of that, the angle is probably 30. All right. So this hypotenuse then is 12 meters. Right? Does that make sense? All right. So this 500 Newton force is going to be applied along this 12-meter distance. Now, one thing I told you yesterday was that the force and the displacement need to be applied in the same direction. Are these applied in the same direction? No. They're not. So that means we need to write an equation for that either figures out the amount of the 12 that's in the same direction as the 500, or the amount of 500 that's in the same direction as the 12. Okay? I like right triangles, do you?
Yeah.
Okay, so let's work with a right triangle then. All right? So I'm going to draw in blue some components or some sides of a right triangle. Okay? This is the x component of the displacement, right?
Yep.
This is the y component. Which one do I need for this problem? Need the y component, don't I? Okay. If this is 30 degrees, what's this angle right here?
That is
60 degrees, right? Because 30 and 60 add to 90 make the rest of that right angle, right? So how much of this 12 is here?
6.
How can I figure that out? We'll call this y here. Okay, so we'll do cosine 60 equals y over 12, doesn't it? Yeah? So that means y equals 12 times the cosine of 60. Okay, I'm just going to leave that like that, but that is our displacement, isn't it? Right? That's our displacement. Okay, I'm just going to hold on to like that because I don't want to lose the cosine of the angle in there. I want to keep that cosine of the angle. Okay, because that's going to be important later. All right? So that to figure out our work done, work equals force times displacement, right? But in this case, our force is 500, and our displacement isn't 12, it's not 6, it's 12 times the cosine of 60.
My brain hurts.
Okay, good. Usually when you work out, things get sore, right? So when we figure that out, what do we get? 500 times 12 cosine 60. What does that equal?
I think 3,000.
3,000. You sure?
Yes.
Okay. So another reason why I like this problem is what this just shown us is that if we went straight up or up the incline, they do the same amount of work.
Yeah.
Right? So that shows us, that reveals something called path independence. Okay? Whenever you're doing work, which is why this is a displacement, not a distance, the work done is independent of the path. It doesn't matter which route you take. All that matters is the displacement that's parallel to the force, right? Now, the reason why I didn't have you tell me this number right away is because when you do 12 cosine 60, what do you get? 6, right? Which is the height, isn't it?
Yeah.
Okay? So a shortcut in this problem is don't worry about the cosine. Just say, well, my force is 500. That's parallel to my height. We'll do 500 times 6. And I kind of shortcutted my way through the problem.
Yeah.
But sometimes when we take shortcuts, we miss the view.
Something.
Right? And the view is this equation right here. Now I'll put a little box around this equation because we're going to use this again in little bits. But the work done is 3,000 joules, right? Does that make sense? Okay, are you guys with me? All right, not yet. So now we need to figure out the work done by Sheldon and Leonard. I want to find this vector right here. Right? In moving the bookcase from here to there, how much work did they do? 3,000 joules, right? We just figured out when they did 3,000 joules. Then when the stairs combined, did 3,000 joules of work, right? So we know that 3,000 joules is our W. Right? What's the length of their displacement parallel to their force? 12 meters. Displacement is 12. Force we do not know yet. Okay? But was Leonard right? The force required to lift is reduced by half. We'll see. Okay? So we are going to plug in to this equation. Work equals force times displacement. So 3,000 equals force times 12. So what are we doing? Divide by 12. 250. Not half. Sure?
That's the force.
Right, that's the force.
You put joules instead of
Oh, I put joules. My fault. Thank you.
then you
Yeah.
gotta do 250 times 12.
There we go. So the force to lift just the box was 500 newtons, right?
Yeah.
So the force to slide the box of the inclined plane is.
250.
So did they reduce the force by half?
Yes.
They did. Now the only reason why I reduced by half was because of the 30-degree angle. Right? If it was a different degree angle, then it would be a different
So
factor.
if it was a less angle, would it be more or less?
If the angle here was
Say 25.
25, then that means this becomes
Bigger.
65. Right?
Oh, okay.
Cosine of 60 is
6.
what is it?
Cosine of 66.
No, cosine of 60 is 0.5.
Okay.
Cosine of 65 is 0.42. So it's going to lower. So the longer, and I should know that anyway, the longer the incline, the less force you need. Okay? You can think about it this way. When you're talking about lines and slopes, right?
Yeah.
If this line is steeper, right, then my change in y is bigger per change in x, right?
Yes.
So then my force needed is bigger because I have a steeper distance. Okay, does that make sense?
Yes.
Whereas if I go more shallow, my force needed per step, per change in y, is less.
Yeah, so I handicap ramps out like that.
So my handicap ramps aren't as steep as the stairs.
Yeah.
Right? Does that make sense?
Sure does.
So the longer the ramp, the less steep the ramp is, the less force required. Right? All right. So was Leonard right?
Yeah.
Okay.
I guess.
Well, Sheldon.
Sheldon, they both were right. Because Leonard said about half, and Sheldon said no, it is half. And
Yeah.
when I first saw that, I was like, "Wah!" I thought it was hilarious. I was laugh out louding. You know, my wife looked at me like,
Can I go to
"Are you serious? That wasn't that funny." And then I did this. And then she looked at me like, "Are you serious? That was 5 minutes. I can't get back." All right, but any questions about this? Yeah, she loves Big Bang Theory. She watched it with me.
No, but you said that.
Maybe she really doesn't.
Yeah, I showed. It improved her why I thought it was hilarious. Okay. Now
Why is math funny?
it's not math. It's math and sitcoms. It's funny to me.
This is it.
All right, and not only was it funny, but they actually used it correctly. All right, guys. So the reason why I boxed this equation. Now, the whole Big Bang Theory thing is great. It gives me a good vessel to teach you a new equation, and that new equation is this one right here.
Yeah.
Okay. What was the 500? Force. What was 12?
Displacement.
Displacement. And what was 60?
Cosine.
The angle twice.
The angle.
That was
Leftover angle.
Oh no, the angle that's up top.
Nope.
Yeah.
The 60 was the angle that's between.
30 and 90.
Nope. That's between the 500 and the 12. Right? So the 60 was this angle between the 500 and 12. Does that make sense, guys?
Yes.
Okay. So this right here, this 60, was the angle between the force and the displacement. Okay? So the equation is work equals force times distance times cosine of,
Angle.
oh, yeah, not 60. My goodness.
Oh,
Theta?
that's.
Angle,
Oh, that was.
cosine theta.
Now I noticed that
Cos theta.
I noticed that you put a asterisk there instead of a dot.
Ah.
It's still facing the
Theta.
same direction.
It's an oval.
The reason why I didn't put a dot here is because the dot product
Yeah.
Math.
ends up finding the amount of the two vectors that are in the same direction. They're parallel to each other. And the way you find that amount is by doing the cosine of the angle between them.
Okay.
So the way you find the magnitude of a dot product is you multiply the magnitude of the two vectors and the cosine angle between them. So that's something that you haven't learned yet. Freaked out, if you will. Okay. But that comes from the idea of the dot product.
Okay.
Right? And now these two are really just magnitude. They'll do the cosine of the theta.
Okay.
All right. Are there any questions?
No, let's get back to
Yeah. Big Bang Theory. All right.
I have a question.
So if this is my distance and this is my force, that's theta. It doesn't need to make a right triangle, but that's my theta. Does that make sense?
Yeah.
Okay. Same thing like in this problem. If displacement's this way and force is up, that's theta. Okay. The angle between the force and distance and displacement is your theta. Alright. Theta is a Greek letter. Okay, it's just a Greek letter that they used. That was a common convention for theta. Yeah, for angle. Kind of like how we just use x and y. X is our general convention for input. Theta is just the general convention for input.
Yeah.
Any questions? Any questions about that equation? None? All right.